Welcome to session Q1, plenary session 2, entitled Treasures from the Cosmic Frontier. My name is Ian Shipsey, I'm the chair of the session. Although we are starting late, these talks are far too important to curtail their length. And so we'll go to the standard length of the talk of 30 minutes for each. We'll then take a couple of questions from the audience to speed up the asking of questions which must be asked by going to the microphones. As the speaker is summing up, please move to those microphones. We'll only have time, however, for several questions per speaker due to the late start. And so the first speaker is Naoko Kurahashi Neilson, whose talk is entitled Cosmic Neutrinos in the IceCube Detector.
Hi, can you hear me? I hope they pay me for this. Good morning. Thank you for coming to my talk, which I'm sure all of you are here for. Well, it's an honor to open for Neil deGrasse Tyson, but also an honor to be telling you, with red in my slides, about IceCube, which has been experiencing, now if I can just find a laser pointer here, which has had a really exciting last couple of years. And so hopefully this talk, I can sort of summarize what the excitement is, what's happening, and what the latest news out of IceCube is. As many of you know, IceCube is a neutrino observatory that operates at the South Pole. Here is a picture of the South Pole at night, which is the same thing as the winter. So it's like this for half the year. I don't know if you could make it out. Here is a building that is a big 3-story building. That's where we house all our computers. Here are some flags so our winter rovers don't get lost going there from the station. And the IceCube detector itself is buried under the ice. And here's a big question mark aurora. And I think that's pretty symbolic that there's a question mark aurora over IceCube. So I like to start with this slide. My talk is about cosmic neutrinos in IceCube. By cosmic neutrinos, what I mean, and I'll also use the word astrophysical neutrinos as well. What I mean by that is we're talking about neutrinos that come from beyond our solar system and in very high energies. So let me start with an energy argument because everybody is familiar with energy. Okay. This is going to be challenging. There's actually a slide here with a scale, here is GeV, which is 10 to the 9 eV, people who operate at much lower energies. I will be talking about units of GeV, TeV, and PeV. Just to remind you, those are 10 to the 9, 12, and 15 EVs, respectively. And I'll just go on. And so the highest energies particles ever observed, and this is from me in the reference frame of the Earth. Sorry, I'm very distracted by this. I hope you guys are too, as much as I am. So the highest energies we've accelerated as humans around here with the LHC. The highest charged particle we've ever seen is in the form of cosmic rays in charged nuclei. In terms of neutral particles, we've seen gamma rays, but last summer IceCube announced, and this is the cover of Physical Review Letters, which is much prettier if you can get it in full color, that we saw a really high energy neutrino at PeV. So this is right here. So now you have to ask the question, we know how to accelerate charged particles, as in the LHC, you have an electromagnetic field, you can accelerate charged particles. But how do you accelerate neutral particles? And then that begs the question, there's an arrow here, is there a connection between cosmic rays, charged particles, and the neutral particles we see? Can the neutrinos be created the same way gamma rays are? So they're both neutral. Maybe they're created the same way and accelerated up to all the way up to those energies. What are the sources? What's the signal? What's the background we're talking about here in terms of neutrino observation? And where do they come from and what do they tell us? So here's the outline of my talk. I'm going to start by making a case for neutrino astrophysics. If you can see the bottom left plot over there as well. Almost all the plots I'm showing today are a log-log plot of flux versus energy. So this covers a large order of magnitude. And in this plot, I plot all the particles we know in the universe in terms of flux and energy. And you see the electromagnetic spectrum and also cosmic rays, these charged particles. And I'll be talking about the very high energy, well, not the very, very high energy, but the higher energy tail of this. But the question is, these high energy particles, where do they come from? What sources accelerate these particles to such high energies in our universe? And then the other question is how? What happens inside the source or around the source such that these very high energy particles get created? And in doing this, it's helpful to look at accelerators in the universe, such as supernova remnants, in different eyes. So here I have the Crab Nebula that's seen in X-rays, optical, infrared, and radio. And you see that you pick out different features of the source. So if we saw this source in neutrinos, what would it look like? And would it give us more insight into how the source environment is? So usually when people motivate neutrino astronomy, you show a slide like this that says, well, here's a source, and here's a charged particle, and charged particles can get absorbed by clouds around the source. There should be a cloud here in gray. Or they can get deflected by the magnetic fields in between the source and us. So you point back to where the charged particle came from, you are not pointing back to the source. But in neutrinos, because they're charged neutral, they point straight back. And also, unlike gamma rays and cosmic rays, they don't get absorbed in interstellar dust or cloud. I think the argument is a little bit more than that. So let's start with the charged particles. Here is, again, a flux versus energy log-log plot of the cosmic rays we've measured. And at low energies, cosmic rays can't escape your local magnetic fields. But at high energies, it can. So the higher energy we go, the far away we're looking. But high energies, as I said earlier, when they hit dust clouds, they interact and deplete. However, when you have a proton-proton or nucleon-proton type interaction, you create neutrinos. So in fact, where these protons or cosmic rays are getting absorbed, what you do is create neutrinos. There's more arguments for the connection between cosmic rays and neutrinos, and that's because we've seen extremely high energy charged particles at 10 to the 20 EVs and beyond. And this is a plot from the IceCube Observatory, which looks for these particles, and they're a very beautiful result if you can see it. But what does that mean? So the fact that these extremely high energy cosmic rays exist, that means that they have come to us traveling through the cosmic microwave background, which is leftover light from the early universe. And what happens by knowing that those two things exist is that they interact. At these energies, the cosmic rays interact with the CMB background. And in doing so, you produce neutrinos. And this is called the GZK mechanism. So we call them GZK neutrinos. So now if you look back to this plot, you can produce neutrinos where cosmic rays deplete and interact with the dust cloud, but also where there's nothing, and you can't see the dust cloud, so this is not going to be as dramatic. Where there's nothing, you can also produce neutrinos if you have extremely high energy cosmic rays because the universe is filled with CMB light. Let's move on to the gamma rays and how neutrino astronomies are connected. A quick shout out to the gamma ray telescope community. There's space-based and ground-based telescopes. This has a lower threshold. This goes up to higher energies. And there's two ways to produce gamma rays, leptonic and hadronic. So leptonic processes, for example, maybe an upscattering of photons by an energetic electron. But this is the inverse Compton effect. But here's the leptonic processes. And then there's another way you can create gamma rays, which is hadronic. So if you have a neutral pion, it decays to gamma rays, two gamma rays. However, in a source environment where you create neutral pions, you probably create charged pions too. And charged pions decay to neutrinos. So if gamma rays were produced via the hadronic process, it's very likely that you're also producing neutrinos via this process. So at very high energies, it's hard to tell apart just by looking at the gamma ray energy spectrum if the source is accelerating or producing gamma rays in leptonic or hadronic processes. But if you see neutrinos coming out from that same source, you can tell that, in fact, gamma rays are created hadronically at the source. So again, we go back to this diagram where gamma rays are created and maybe neutrinos are created too. So the picture is a little bit more intertwined than just saying that neutrinos can point straight back and they're not depleted. There's also a very, very good, what's the word I'm looking for? Very good correlation with cosmic ray astronomy and also gamma ray astronomy. Why high energies? I said IceCube looks for very high energy neutrinos. Why high energies? So again, this is the flux versus energy log-log plot, but this time I've multiplied the flux by e squared. So a straight line here means that it's actually decreasing at e to the minus 2. Right. So if you plot the neutrinos you should be able to see here on Earth, what you expect is this. You expect a large background from neutrinos created in the atmosphere, which I've shown in black, and that goes down very quickly as you go to higher energies. For neutrinos created in astrophysical objects, we expect that they follow roughly a e to the minus 2 spectrum. So as you go to higher energies, you see that you win in signal over background. So there's one reason you will go to higher energies. You see at the end, you see the GZK bump. This is, again, the neutrinos created from interactions with the CMB. So my talk is going to be in the energy range where we are interested in, where we think we win in signal over background compared to atmospheric neutrinos, but I won't be talking about the very high energy GZK neutrinos in this talk. I said neutrinos are great because they don't interact, they come straight at us. That's great, but it also makes them hard to detect, so it's a double-edged sword. So here is the interaction length, the amount of material it takes to make a neutrino interact versus the neutrino energy. And now I know you can't read this, but at 10 to the, I have to read it myself, at the very end is 10 to the 21 EV. So a 10 to the 21 EV neutrino going through the critical density of the universe travels about 10 to the 34 centimeters before they interact, at 10 to the 21 EV. However, our observable universe is about 10 to the 28 centimeters. So the universe is not even long enough to stop these 10 to the 21 EV neutrinos. If you come down to somewhere very dense like the Earth, you do better. So now we can stop neutrinos in a shorter distance than the Earth's radius at about energies above 10 to the 12, 13 EV. So neutrinos are hard because they don't interact. In some ways, I like this because I'm an experimental physicist, and so, you know, the challenge with, I think the challenge with gamma ray and cosmic ray astronomy is that you can detect the particles, but then you have to unfold what happened between the source and you. Things happen, interactions happen, deflections happen, so you have to unfold that. Whereas neutrinos, it's hard to detect, which is an experimental physics challenge, but once you detect it, hopefully it's easier to interpret. So that is my kind of challenge. So let me tell you a little bit more about IceCube, the Neutrino Observatory we work in. Again, it's located at the South Pole, the geographic South Pole. But please download my slides. This is a beautiful picture of the South Pole, aerial picture of the South Pole. Here's the station. The geographic South Pole marker is somewhere around here. Here's the skiway where our planes land with skis. And over on this side, this is kind of the footprint of IceCube because it's buried underneath the ice. So if you take a segment and look at it straight on. Oh. Hi. Okay. So here's the surface. If you go to the South Pole, of course, Antarctica has a continent, so there's bedrock in the bottom, there's a continent. And then there's about 3 kilometers of glacial ice on top. And we live up here, and what we did was we drilled down, all the way down, to get to this deep, clear ice, and instrumented a cubic kilometer of ice. We instrumented them with our photon sensors, which we call DOMs, or digital optical modules. They're PMTs looking down and read out electronics also embedded in this pressure sphere. And you can't see, but each one of these dots is a DOM. So we have very many of them. What else can I tell you? So if you bury yourself in 2 kilometers of ice at the South Pole, 3 kilometers of ice at the South Pole, what do you see? You don't see anything because it's pitch black and dark. The surface light does not get down that far. But you will see once in a while is Cherenkov light from particle interaction. So IceCube sees this as well. Again, each one of these white dots is our digital optical module, DOMs, or optical sensors. So here I've shown the amount of light each DOM saw with the largeness of the blob, and also the color is time scale. So red is early and blue is later. So if you see a light go through like this, that's from muons. And so you can see the track being reconstructed of muons. So if neutrinos is a muon type neutrino and has a charge current interaction, you produce muons, and we see that as tracks. In all other interactions with all other neutrino types, and also the neutral current interaction with muon neutrinos, we see showers. We see particle showers, but because our scattering length is small and we see a lot of scatter in the ice, the particle shower looks to us like a blob of light, just a sphere of light. At very high energies, charge current new tau interactions are thought to be interesting, but this is beyond the scope of this talk, and we haven't seen this, so I will skip it for now. Oh. IceCube has a very, very rich physics program. You'll just have to take my word for it. We do a lot of things: cosmic rays, atmospheric neutrinos, particle physics, astronomy, cosmology. If you can see, the black circles are to represent talks that are present in this conference. Something that may be of interest to a lot of people in this room is that IceCube does neutrino oscillations now at 20 to 30 GeV. So this is new. Please talk to the people. I'll show a list of IceCube talks at the end. Hopefully you can see them, and please find the appropriate talk you want to go to. Well, this slide's not going to work. So the reason why we can do such a diverse and rich amount of science is because we have a fairly large collaboration of about 250 people from 40 institutions from around the world. And so let me move on to observation of astrophysical neutrinos. So astrophysical neutrinos, although I think almost everybody believed that they existed, that these astrophysical objects emitted neutrinos, we had never seen them until last November. We made the cover of Science magazine. And here is a event. I have to stop saying that, I'm sorry. Here's an event that we saw in one of this analysis that discovered cosmic neutrinos. So you can see there's an interaction. A neutrino sneaks in because neutrinos don't emit light, and then has a big interaction here. You can see the shower here. And then this was of a charge current interaction with a muon type neutrino. And I know this because you can see the muon leaving the detector this way. So, and that is an extremely high energy event. It's over 100 TeV. So how did we discover these excess events? So here is a plot of the number of events versus the energy we saw in our detector. The hashed line summarizes all the backgrounds we expected, and the crosses represent data that we saw. And you see that we see excess of events. And I should say that in our science paper, we showed this plot with 662 days of data. Today I'm showing 3 years of data, so we updated this to 988 days, and the case remains the same. In fact, we have a stronger case now that we see astrophysical or cosmic neutrinos for the first time. So I said we saw excess events. Excess to what? So what should IceCube see as background anyway? So here's the Earth turned upside down. IceCube is at the South Pole, so now it's on top. And cosmic rays that bombard our Earth's atmosphere creates showers in the Earth. This happens all the time right outside our window. And the shower components, some of the shower components are atmospheric neutrinos and atmospheric muons. So both of those things can come to our detector and mimic astrophysical neutrinos, cosmic neutrinos that come from further away from the universe. In the northern sky, and the northern sky at the South Pole means upcoming events to us, muons can't travel all the way through the Earth, so we only get atmospheric neutrino backgrounds. So in blue, I show the atmospheric neutrino background, which we expect from all over 4 pi. And then on top of that, so this is a summary plot, this histogram is stacked. On top of that, there are some atmospheric muon backgrounds that we expected. So that's the red. And so that's the summary of all the backgrounds. And there's another actually special atmospheric neutrino background that I won't get into today, but Nathan Whitehorn has a talk later in the afternoon. He will elaborate on that as well. So we see more than we expect from background. How did we get this data sample? And so the way we looked for these high energy events is not just to say, okay, give me the highest energy events I see in 2 years of data, but also require that the event started inside our detector. So if you think about the difference between neutrinos and muons, muons continuously emit light as they travel through, whereas neutrinos sometimes can sneak in, interact inside the detector, as you saw on the science cover, and then leave emitting light. So that way, if you have a veto region at the outside of your detector, you can discriminate between muons and neutrinos. So if you require that not only the events be high energy, but also pass the veto region in darkness and then emit light starting inside the detector, that's how you get our data sample that I showed there. And again, Nathan will talk more about this analysis that discovered cosmic neutrinos this afternoon at 3:30. So the axis we see, we can fit an e to the -2 flux to it because this is, again, the model, the signal that we expect, and it fits quite well. It fits to the level of 10 to the -8 in these units for the signal neutrino. So this is great news. The neutrino astrophysics, this is great news. We found cosmic neutrino flux. We found excess flux. So now the astronomy question is, so what are the sources? Where do they come from? In order to do that, we have to reconstruct these events and point back to where they came from. The sample is dominated by showers, and it's very hard to do shower reconstruction. As I told you before, there's a lot of scattering, and it looks like a blob of light to us. If we do this carefully by taking each waveform of each PMT and doing careful fits, we can reconstruct it to about 15 degrees if the event is about 100 TeV in energies. If you have a track coming out, as I showed you earlier, then we can reconstruct it to about 0.5 degrees. So this is a mixed sample of both track and showers. And Jake will tell you more in the next session in room 202 about this analysis. We mapped all the events we see in this high energy sample. And then we did a likelihood analysis to see how clustered at every point in the sky the events are. And so this color scale here represents the clusteriness or the likeliness that there is a source that contributed to multiple clusters of neutrinos there. Unfortunately, we don't see any clusters of any significance. So we have not really resolved a source in these data samples. Let me tell you another way to look for these astrophysical neutrinos. And now that one was very low statistics and low background. This one is going to be high statistics and high background. And for that, we use charge current muon neutrino interactions because you get these nice tracks which you can point to. And in fact, at about a TeV, we can have about a degree angular resolution, and at a PeV, less than 0.5 degree angular resolution. So another way to get rid of the muon backgrounds is to say, okay, I just want the ones that are energetic, that points well, and give me the ones that come from below my feet at the South Pole, because they can't be muons because muons can't go through the Earth. So you can collect all upgoing muon-type neutrinos, and in fact, Chris, the student who's giving a talk this afternoon about his analysis, has done this. So here is a reconstructed zenith angle versus events plot, and you can see that -1 is cosine -1 would be the events that go straight up through you at the South Pole and to the horizon. And he's collected 35,000 events, and you expect very little muon contamination from those events, and plotted the energy and found cosmic neutrinos yet again in this very independent analysis in an independent channel. So again, the black are data points, and the backgrounds are in green, and you see again at high energies, and high energy excess is important because that's where we have good signal to background. We see excess at very high energies. And Chris will also go into details about what his analysis saw versus what the low statistics, low background analysis saw, and if the flux are compatible and things like that in his talk in the next session in room 202. So I come back to this slide. It's great. Neutrino astrophysics is great. We discovered astronomical neutrinos, astrophysical cosmic neutrinos, but where are the sources? And again, Jake will also tell you about this sample. Here is another sky plot, and again, this is in test statistics, so the colorful, more yellow it is, the more clustered our events are, and more energetic our events are, and he looks for point sources using a method that he'll describe, and again, we don't see point sources. So the fact that we've discovered a diffuse flux, but we don't see a point source, you can say something about the sources we're dealing with and looking for these neutrino sources. And here is the limit, if you will, from Jake's analysis for point sources. So the way you read this is at this declination, if the source had this much flux, we would have seen it in Jake's analysis. And so the fact that we don't see it says that, okay, at least these point sources, these individual sources, the fluxes are below this level. But we do measure a diffuse flux. And this is about a factor of 15 apart. So what that means is that we probably have in the northern sky of order 15 sources we are dealing with. In other words, the diffuse flux we measure, the cosmic neutrinos we measure, they don't all come from a handful of sources, unfortunately. Marcus talked about more connections, such as with gamma-ray astronomy, like gamma-ray sources on Saturday. If you missed his talk, this is what he looks like, so please look for him. So let me summarize the status of cosmic neutrino observation. The low statistics, low background sample, we see diffuse flux. That's great, but we don't see sources. We don't see clustering. A high statistics, high background sample, and this is a new result this conference, we see diffuse flux again, but we don't see evidence of clustering. So that leads us to think that maybe there are multiple sources distributed isotropically in the sky. So I have 3 minutes left. Let me say a few words looking forward. If you go to your if you go to your astronomy friends and tell them that your neutrino astronomy catalog only has 2 sources in it, they will laugh at you. But unfortunately, this is the state that we are in. So the 2 astronomical things that we've seen in neutrinos is the sun, which is incredibly close, and also a supernova in 1987. This wasn't a directional detection. This was just a surge at the right time when the supernova went off. And this is both at very low energies for us in MEVs. So we want to add more sources to that neutrino astronomy catalog. And we need a lot of events. As you saw, we operate at this very high energy tail where statistics is not enough. But we are only talking about the first 3 years of IceCube data here, and we'll run for longer. But maybe we can build a bigger detector. So this is something we're starting to talk about. Maybe if the existing IceCube detector is in red, we can build a much bigger, sparser detector. So design studies are on the way. There is another future Mediterranean several cubic kilometer scale type telescope planned. Let me conclude by saying history is on our side. And what I mean by that is this. If you think about gamma ray astronomy, which we take for granted that it is astronomy nowadays, it started from a measurement of a diffuse signal, and then it started resolving sources, and now we think about gamma ray catalogs as, of course we have gamma ray catalogs in astronomy. But it all started with a diffuse celestial radiation measurement in a rocket in the 70s. And then in the 80s we started resolving gamma ray sources, and now we have a very big catalog. The analog for X-ray astronomy is even more interesting because the first source detected in X-rays was the sun. And then the diffuse emission was measured, and the first non-solar source was measured. And of course, we have a beautiful X-ray catalog. So hopefully, in the near future, I can come back to you and say, we've measured the first handful of neutrino sources, and hopefully before my career or my life is done, we can get to a point where we talk about neutrino astronomy catalogs, like, of course, there's neutrinos in astronomy. So let me conclude by going back to my outline slide. I think the case for neutrino astrophysics is convincing. IceCube is finally complete. You're seeing the first 3 years of data here, and there will be more to come. The first observation of cosmic neutrinos has happened, and we're very proud of this. We see cosmic neutrinos in all flavors, in all sky. In this conference, we also see them in the northern sky with the muon neutrinos, which is these pointing neutrinos that we always assumed might be the golden channel to do neutrino astronomy. So we are in a very favorable condition. And I think looking forward, the hunt for the first neutrino source is on. So I will just leave this up to make sure that you go to all our incredible talks. Thank you.
That was terrific. We have time for just a couple of questions. You have to move to the microphone if you wish to ask a question. There's a microphone on the right and a microphone on the left. Anyone have a question? If you do, please move to the microphone. Yes, please, that one there on the right.
Yeah. So what is the highest energy neutrino that you could possibly detect with this current configuration?
We can certainly detect as high as they go. The question is, where does the cosmic accelerators run out of steam? And also the coupled answer is, because you're operating on this flux versus energy plot where it goes down, the higher the energy, the rarer they are. So how kind nature is to us in sending us high energy neutrinos, I think that's our limitation.
I take the question on my left.
How many neutrinos, cosmic neutrinos, have you seen in 3 years now?
Yes, so we have seen 37 events in our low background, low statistics sample. And we expect, I think, 18, 17, 10 of order that, 10 to 15 backgrounds in that sample. So if you subtract that, that's probably the number we're looking at. Unfortunately, we're not in a regime where we can say this one specifically is cosmic, and this one specifically is background. We can do some guessing games with probabilities with that, but it's a hard game to play.
Take one more question and that's the end.
What is it about the different kinds of neutrinos that makes one trace through your detector and one scatter?
It's just the type of detection, the interaction. So, okay, maybe I should say muons are long-lived. So muons can travel through the detector and not lose all their energies, whereas showers, the shower components are short-lived, so the shower dies down very quickly. And if you compare that to the length scale of our detector, I think that's the topology that we get.
Okay, let's thank Naoko again.
Thank you.